Okay, there are two more topics that I'd like to talk about with respect to discrete time signals, and that is signal classification and signal decompositions. There are a variety of ways to classify signals. The first way to classify signals is to compare them as deterministic versus stochastic or random. So a deterministic signal is one that is determined by a mathematical formula or a table or some other rule that allows us at any time, any value of the independent variable, we can either compute or look up the value of the dependent variables. Those are deterministic signals. A stochastic signal, or random, is governed not by a mathematical formula, but by often a physical process that introduces randomness. An example would be a speech signal. This is not one that is, over a short interval, we could describe this as perhaps a very high order polynomial or something else. But in general and in the long term, you cannot come up with a mathematical formula for this waveform, for a speech waveform. So we'll call that a random or a stochastic signal. On the other hand, this linear frequency modulated chirp signal is a mathematically precise signal, and so it's deterministic. Here are a few examples in 2 dimensions. A checkerboard would be a deterministic signal because at any point we could have a rule that tells us whether the pixel value is black or white. Similarly, fractals are deterministic because there's a precise calculation that is performed at any pixel location to determine the value of the image at that point. On the right-hand side here, I'm showing a photograph that I found online that I'm going to call a stochastic signal. You might look at this and say, well, there's sort of a periodically repeating component because these houses repeat and their images are reflected in the water. But if you were to revisit this scene at another time, it would look very different because the water might be disturbed, the clouds would be different, the illumination would be different, it could be day-night. I mean, there's just no way to predict in advance exactly what this will look like. Who knows? Maybe there'll be boats and birds, and maybe there'll be rain, maybe there'll be snow. We just have no idea. Maybe there'll be an ice fisherman out there pulling a fish out of a hole in the ice. It could be anything. So since it's not predictable, it's random. Now, in this class, most of the work that we'll do with pencil and paper will involve deterministic signals, signals that can be described and systems that can be described mathematically. But in real life, most of the signals that you deal with will be stochastic or random. And you cannot, using pencil and paper in advance, calculate the values of transforms or outputs of systems driven by stochastic inputs. And so an important component of what we will do in this class is, in addition to learning how to do hand calculations with pencil and paper, learning how to code those same kinds of calculations on a computer so that we can use a computer to do calculations on signals that don't have mathematical descriptions. The next way to classify signals is using a repeating structure. So in this case, I'm describing this in the setting of continuous time signals, but of course the same applies for periodic signals, and we'll have more to say about this later. But the definition for a periodic continuous time signal is shown here. If you delay by any integer number of periods, or advance by any integer number of periods the waveform, you'll reproduce the waveform exactly as if there were no time shift. That's a periodic signal. An aperiodic signal is one that has no repeating patterns. And so you can see I've shown a sinusoidal waveform that's periodic, and maybe a Gaussian kind of a bell curve that is aperiodic. Of course, as we have seen previously, periodic signals can be constructed from aperiodic signals using convolution with impulse trains. Here is a signal that's constructed by a delayed, infinite number of delayed copies of a basic pulse P. And you can do the same thing in discrete time. Here I've chosen to represent the periodic discrete time signal in a slightly different way. This is maybe a little bit more practical for us to think about from a computer implementation standpoint. Let's suppose you want to produce computer-generated music, and you know what one period of that sound should sound like. Well, you might even have tabulated the values in that one period of the signal. Then you can index those. So let's suppose the table has size 100, so capital N here is equal to 100. Then to generate the signal at any time, you take the index modulo 100 and use that to look up into the table and to produce the output sample. So again, it's deterministic and it's periodic with period n. So this would be maybe one way you could generate music using a computer, and you only ever have to store, you don't have to store an infinitely long signal, you only ever have to store one period of that signal. So it's very practical. Another way to classify signals is as being finite or infinite, and this has to do with the duration or the region of support for the signal. We could talk about signals that are doubly infinite, that go from minus infinity to plus infinity. They're defined everywhere. A semi-infinite or one-sided signal could be a causal signal that starts at time 0 and moves to the right, or maybe a signal that is defined at negative times and is 0 after time, sometime n naught. A finite duration signal, this might be like a digital image that has two indexes, and both of them are finite. They exist from over a finite range, finite support set, and it's maybe not even defined outside of that support set, like a digital image. Even music. Suppose you play your favorite song. Well, it may contain millions and millions of samples, but it's still finite. A semi-infinite signal might be your favorite song played on repeat forever from some starting time. So that would be maybe a semi-infinite or a one-sided signal. This leads us to the idea of causal versus non-causal. So a causal signal is one whose support set is to the right of 0, and anti-causal is one whose support set is to the left of 0. You could have other kinds of signals that we could call right-sided. You could have causal right-sided signals and non-causal right-sided signals. Still, these would all be considered right-sided. And you could have left-sided signals as well, as shown here. So we have causality that we can talk about, and we have sidedness, either left-sided or right-sided. Another way to characterize signals or classify them is as being bounded. So the formal definition of a bounded signal is if there exists an M, some bound, finite bound, such that the absolute value of the signal is below that bound for all time, then we would say that the signal itself is bounded. Otherwise, it's unbounded. So here are some examples. A sinusoid is a bounded signal. Here you see that depicted down here below. The bound is 1, it never exceeds 1. Another bounded signal is a causal decaying exponential. Here you see it right here. Again, the bound is 1. It's 0 before time 0, and then it peaks up to 1 and then decays thereafter. So it never grows in an unbounded sort of way. A two-sided or doubly infinite exponential signal, in this case e to the minus t, this blows up as we go towards minus infinity. So we cannot say that this is a bounded signal. It would be unbounded. Another example in discrete time is a sequence generated in this way with these initial conditions, and you may recognize this as the Fibonacci sequence. This is a sequence that grows without bound as we perform the recursion, so it's unbounded. We can also classify signals by their symmetry properties. We could have even signals. An even signal is one where if you do a time reversal, you reproduce the signal. An odd signal is if you do a time reversal, you also invert the signal. We see examples of these over here. A real signal is one such that if you conjugate, you make no change. So a unit step would be an example. A pure imaginary signal is one where if you conjugate, you change the sign of the signal, and I believe this is an example of a purely imaginary signal that obeys that property. We also could talk about Hermitian signals. This is one where if you conjugate and time reverse, you'll reproduce the original signal. And then you could also have anti-Hermitian signals, one where if you conjugate and time reverse, you get a negated version of the original signal. So these are all symmetry properties that we will encounter. And again, it's another way to classify signals. Another important classification is the ability of a signal to be accumulated. And there's different ways to accumulate. You could accumulate the absolute value of a signal. You could accumulate the squared values of a signal. You could accumulate the squared values and then average those values. And so we have different categories of signals. We have signals if the absolute sum, so this is called the absolute sum. If the absolute sum is less than infinity, then the signal is absolutely summable. A delta function is absolutely summable. A sinc function is not absolutely summable, but it is square summable, or we would say it's an energy signal because the sum of the squares of the absolute values of the signal is less than infinity. What are examples of power signals? Power signals is if this average energy is less than infinity. Well, constants are power signals. They're not energy signals, but they are power signals. Sinusoids and complex exponentials, step functions, are power signals. And so it's important to be able to classify a signal. A decaying exponential is absolutely summable. So for all the signals that we've looked at so far, we should be able to classify their summability properties. And now here's a summary of these different classification attributes. You have predictability, it leads to deterministic or random. Repeating structure, we have periodic and aperiodic. If the support set can be finite, semi-infinite, as in causal or anti-causal, or left-sided and right-sided, or it could be infinite, as in a two-sided, doubly infinite signal. Amplitude limits, you could have a bounded or an unbounded signal. Again, we have causality and anti-causal and so on. We have symmetry properties, and we have summability properties. So these are all things that we should keep in mind. Preferably, these sorts of definitions and properties, attributes should be memorized. Finally, let's talk about some signal decompositions. One of the ways we can decompose an arbitrary signal is into its even and odd components, or its parts. So, so we can either represent a signal as a sum of its even and odd parts, or we can decompose that signal into its even and odd parts. And so here you have sort of a synthesis formula on the left, and on the right-hand side are the analysis formulas, where we take a signal and we extract the even part and we extract the odd part. So here's just a graphical example, a simple example where we have an arbitrary signal x of t. Here is a time-reversed version of x of t. And so if you look at how do we get the even part? We take the signal and add it to its time-reversed version, then divide by 2. So if we take this signal and add it to this signal, we end up getting this other signal called the even part. The odd part is the difference of a signal and its time reversed version. And so if we subtract these two, we would end up getting this odd waveform here. Odd signals will always pass through the origin. And so the interesting thing is that if we, in terms of synthesizing the original signal again, we could resynthesize that signal by adding together these two, the even part and the odd parts. And you can see that actually does happen. Look over here at the far left. If we add this little step to this negative step, we're going to get 0. And then as this ramps between that point and this point, this one ramps between here and 0, so that by the time we get to 0, we're fully ramped up. And so that gives us this little ramping portion. The same sort of thing happens over here on the right-hand side. If we add this ramping down to this ramping up signal, we see that we get this, we reproduce this square on the right-hand side. So that's the even and the odd decomposition. Another way we could decompose or represent signals is by their real and imaginary parts. One way we can build up a complex signal is by adding the real part plus j times the imaginary part. How do we compute the real and imaginary parts? Well, the formulas are shown here. You add, to get the real part, you add a signal to its conjugate and then divide by 2 to get the imaginary part. You take a signal and subtract its conjugate and then divide by 2j. You divide by j to get rid of the j on the imaginary component. So that's the real and imaginary decomposition. You can also do a Hermitian and anti-Hermitian decomposition, which is kind of like the even and the odd, and like the real and imaginary. It really kind of combines those two. So for the Hermitian portion of a signal, you add a signal to its conjugated and time-reversed version. Notice that for the real and imaginary, we did not do any time reversals. And for the even and odd, all we did was time reversals. So here we have time reversals, no conjugates. Here we have conjugates, no time reversals. And here we have both conjugates and time reversals. So this is how you calculate the Hermitian part and the anti-Hermitian part, and then reconstruct the signal from its Hermitian and anti-Hermitian parts. And then if we combine those sorts of things, we could come up with a four-way decomposition of an arbitrary signal by computing its real even part, its real odd part, its imaginary even part, and its imaginary odd part. And we'll see that later on when we talk about the Fourier transform that it operates in a special way on this four-way decomposition.